So you made it so it's like double.
I have no idea. I know Benji's here because I saw him in Mandarin. Oh. Whoa, yo, 4万。
Okay, so down a few today. Never mind.
Are you okay?
What?
Are you okay?
Does it look okay?
Okay. Oh. Wow, I guess the tables have turned. What happened?
Not a lot, just failure.
Okay, what happened with the needle?
Get my base my glasses. Fixed them. Unfixed. It's electrical tape now, and I had to print out the paper that was due.
Hey guys,
Lotion.
just listen. You can finish the thing up later. That's it. We don't need to. We don't need to. Yeah, we don't need to pretend, right? Finish the thing up later. It's fine. But we need to talk because we don't have very much time. We have a day and a half until. This is what?
This really small sounds so
No, it is not literally. It is literally a week from today. So,
I'm not tense.
let's see. First of all, slides. Let's talk about the slides. Because it's a pain to do otherwise, I would like the slides organized by group, just as you did. I feel like you guys probably already had your Google Drive and stuff all set up. So, and if not, no big deal. Well, let's go ahead and do this by group. So if you can just do probably a Google presentation if you want to do some other way, I don't care, but the Google presentation seems easy enough. We don't do much in the way of animations and stuff and physics, so I think you don't need to worry about any special effects.
Can we do a bunch of animations?
That's an interesting question, mainly because my plan was to download it locally so that I didn't have to worry about communications problems in the lab. I should be able to connect to their internet, but I don't want to deal with that. So I was going to download it locally. It means it has to be a PowerPoint file, which means the animations might not convert right. So here, I'll make you a deal. If you give me a PowerPoint file, you can put what you want in it within reason.
I've done an entire movie in
Define within reason.
If you get a PowerPoint file, then you can put animations in it. I will check first to make sure they are reasonable. However, but if you just give me a Google slide, I'll just download it as a PDF and then save this, which is fine. Just work with slides. I guess I can apply to a PPT; it'll probably work okay. But sometimes the files get thrown off by that one, so PDFs are safe. So I'll leave that up to you. But whatever it is, I just want 3 of them so that I don't have to assemble. I used to do individual slides, then I had to assemble them myself. So I don't want to do that. Okay, each slide, you get 1 slide per person. Each slide has someone's name at the bottom. And do put slide numbers on them. They happen automatically. If you don't know how to do it, check online. Okay, but you should be able to get automatic slide numbers on it. Physicists like slide numbers a lot. Okay, so put slide numbers on them or they'll be mad at you. So, you know what I mean? Slide just 1, 2, 3, 4. Because that way if they want to ask a question, they'll be like, go back to slide 23, like that. So, okay, 1 slide per person plus a title slide and optional conclusion. Okay. Title slide anyone can do, optional conclusion would have to be handled by the last person speaking, and that, like I said, is optional. If you want to just end with, and this is the resolution of our muon detector, and that's fine. There's not a ton more to say. But if you want 1 extra slide to do a conclusion, you may. Yes.
So is there a specific way you have to organize?
There's a specific way. I recommend going in the order that we did. That's the one that makes most sense. Let's say you can't understand your detector if you don't know what kind of particles are colliding, right? So I would go accelerator, detector, accelerator, and then tractor, calorimeter, muons. It's a standard way. If you have some real clever way you want to do it, okay, give it a shot. Because remember, I am grading these, but the real grade is not from me, right? It's from our physicist friends who will be looking So, that's sort of, I'll leave that up to you if you can think of a more interesting way to do it. Now, it's one slide per person. The division of labor is therefore a little bit ambiguous in places. In particular, the spreadsheet person, you know, don't project your spreadsheet. Please don't do that. Okay. Remember and you don't want to go into a lot of detail on the budget because that's just not of interest. I mean, you can say budgetary reasons made us do this instead of this, and everyone will understand that. But like, don't go into detail about how this adds up to 4.2 billion if you put in the other part of that. Like, that's not really. They want to know the physics, right? Not the budget. They understand there's budgetary constraints. That's all they really need to know. So because of that, you need to focus on things that will convince a physicist that to like your detector, right?
Money.
So focus on physics. Focus on things like resolution and that we've talked about that you've measured and calculated, right? Focus on the design and good physics motivations for the design, right? That sort of thing. Now, slides in physics should have text on them. Okay? In fact, they should have enough text. The general rule in physics is enough text so that I can read through it without. I don't need to see the presentation to know everything important there is about the detector. Okay? I know history sort of has the opposite approach, and that's fine with that. But for physics, you should have basically the slide should be all the information should be on the slide somewhere. What you did for your advertisements has about the right amount of information. Maybe go a little more professional. Or like professional physicists and not professional other things. So yeah, but I mean, you probably want to go with more. If there's something wrong, physicists laugh like anyone else, and they're not super uptight, but like they only care about the physics, right? So if you do other stuff, you might make them laugh. They still won't get you. It still won't get you. Won't win you any brownie points. Or maybe it'll only win you brownie points, which are not the same as actual points. So
you underestimate my
in general, don't try. I mean, you don't try and do stupid things like focus on trying to get a good persuasive business case out there. Now, you'll have to spread things out a bit because there's only so much to say, right? So possible things to split things because you have the write-up and the spreadsheet people. Those two people kind of overlap a lot. Right? So you have to figure out how to split between those two people in particular. The resolution person is kind of straightforward one, right? You can divide things as you see fit. Just make sure each person gets a slide with unique information because you don't want to be repeating yourself. You're all going to go in order. Yeah.
So like, how much time should each person be speaking, and how much should be like?
We're aiming for 30 seconds.
Oh, okay.
Okay, though some people will probably take longer, and that's fine. And some people will actually possibly take shorter, and that's also fine. I'm not grading on time. I am grading on good presentation, and I understand sometimes there's not a ton to say. Right?
Should we be using note cards?
You probably don't need them. If you feel like you need them, it's fine with me. Physicists rarely need them, and the reason is because you know what you're talking about, and they're not big on presentation. They just like to talk about stuff. So I think you'll find you won't really need it by the time because everything's on the slide. So there's like not much to say that's not already on the slide. So yeah, you don't have to worry. Probably don't have to worry about it. But if you want to use it, it's fine. Yeah.
Since our audience is a physicist, like I'm just a little bit concerned if like we explain things that they already know.
Right. Do not explain how an accelerator works. Do not say RF, which stands for radio frequency. Like they know all that. Don't be like there's this small particles called muon. Right? Like do not do any of that stuff. Right? They know all that. What you want to explain, you assume that. So imagine you're explaining it to me. Okay, this guy knows as much as I do. Actually, quite a bit more. I'm pretty sure. So you don't need to explain that, but you do need to explain reasons, and the reasons are in terms of physics. So you say, so it's perfectly fine to say pixels near the mean height to get higher resolution and account for the high multiplicity of tracks, right? That is something you would see in a physics presentation, right? You don't want to say high multiplicity of tracks. You can say because there's a lot of tracks, and that's fine too. Okay, but like to explain things in physics terms is good, right? For resolution and measurements and things like that, you should explain those. Not in crazy detail because we don't have that kind of time, but like a quick explanation of what you did, right? Like the thing with the circle and so forth, so that the guy knows what the guy, or excuse me, shouldn't assume there's plenty of women in physics, the physicist knows that that the way you did this calculation for resolution. Otherwise, it's not like you picked a number out of nothing, right? So, and it would be nice if you could say that your resolution is aided by some feature of your detector, right? The fact that we have an extra large muon, our muons are extra large, give us a good lever arm on the momentum measurement or something like that, right? That would be a nice thing if you can say that sort of comment, right? Those are all things that are persuasive and persuasive in terms of physics. So you don't need to explain any terms. All the terms are well known. But you need to explain what you're doing. And don't worry about being redundant there. Like, it's okay to say protons colliding create a big mess and are much messier and have a large number of particles compared to muons. That's fine. And he knows that, but he or she, knows that, but it's still fine. And you'll see that in regular physics. What you will not see is a proton is made up of 3 quarks, right? So you don't do that. Yes?
So for the advertisements, you made the slides like aesthetically appealing. Do we need to do that?
You should make it aesthetically appealing in a more professional way, closer to what you did in like MSI or Intellivium or something like that. The MSI ones I saw that I see were all fine. So slick, clean, professional. You probably want a consistent, what do we call it? Theme. Thank you. You want a nice consistent theme that looks good. Don't need to go fancy on it. It's not going to win you any points. You want it to look clean and professional, easy to read, easy to understand. That's what you want, right? If you get that much, anything you do beyond that is not going to win you anything with a physicist. Physicists are very practical about these things. Like I said, he might laugh. He or she might laugh, but won't give you any extra credit for it. Okay, does that make sense? On the other hand, they're not like super friendly, so you want to put in a joke, you put in a joke, or whatever. Okay, you good? So tomorrow, what I want is a single presentation. Well, I want 3 presentations, right? One per detector group, and then we will be ready to go to further. Okay, a few words about Monday. So, a few quick words about Monday. Then we need to do some more physics. I know, right? Crazy. But a few words about Monday. Report time is 8. Because what is absolutely vitally essential, we're not going to leave right at 8. What is absolutely essential is that we got to run through it. So I'm going to reserve a room. I still need to pick one. Last time I did acquire a room, that worked okay. I'll see if that'll work still. I have to check the schedule. But reserve a room. We'll meet there. We'll do a run through. We need people there on time because and I am taking roll. But it's still a roll day. It still gets entered into the attendance records. So you'll be there on time. So we're meeting at 8. We're going to do a run through. We'll get on the bus and go to the lab. Then at the lab, we're going to tour a bit, and then we're going to have a time. We're going to go to one of their actual conference rooms, probably Curia 2, which is one of the ones that use for a lot of these things. And then we're going to go present to the physicist. Then he or she will give some comments, and then state the winner, and then we'll have lunch, and then we'll go do more touring, and we'll go get to see D0, which is, I think for this group, this class, it should be the highlight of the tour because D0 is an actual collider detector. And you get to go into the Tevatron tunnel and see the Tevatron, which is probably one of the only times in your life, even if you go into particle physics, it's one of the few times in your life to actually get to see a superconducting collider. There's not very many of them in the world. And you don't usually get to go near them because you can't be in there while it's on. You like die. So
I didn't care.
What? Yeah, it turns out if you're radiation certified, you should have learned that you don't go into radiation enclosure, right? But you also get to see D0. The tracker will not be visible. It's too far in the middle. You get to see the calorimeter and the muon system and the trigger chamber and all sorts of other stuff. So it's pretty cool. And D0 managed to salvage part of the CDF silicon detector. So you can actually see the CDF silicon detector like separately. It's just sitting in a case somewhere. And so you can actually see the whole silicon detector, see what it actually looks like. It's pretty cool. All right, don't dress up. That's silly. Physicists don't dress up. Like for anything. And so don't dress up. Like you see what they had to do that for the Fermilab slam, the physics slam for Fermilab. All the people there were like, they're like, no, you can't dress up. Like dress like nice casual. How they got it? They thought like they didn't know how to tie on or anything, right? Because that would be like that'd be ridiculous. Like I don't take you seriously that. So don't dress up. Go ahead and bring things to take pictures with, whatever, right? Don't be on your phone like playing games or texting, but by all means take pictures. This is not a secret laboratory. And by all means, and be good as students, ask questions and stuff, impress people, all that. Right? It's a cool trip. It is mainly intended to be fun, but we are going to have that, that little presentation there, that little final maybe percentage of grade presentation there. Yeah.
For the presentation, is this the numbers that we're presenting or what we got? If anyone did something wrong or the numbers over or under, are you gonna do accuracy checking them?
I would love to. But let's be honest, probably not.
Thank you.
But by the time your kids take this class, I'll probably have the program done. Maybe. Or grandkids, possibly grandkids. Okay. I'm assuming by then the retirement age will be up to 97. I don't trust that.
All the same answers.
Yeah. No, the fact is they're anyway. When I first taught that class, I'm like, oh shoot, what am I getting myself into? I'm not a CS major. I programmed for a few years in grad school, and that was it. I'm going to be I'm going to have all these whiz kids. And I discovered, no, actually, you guys aren't very good I have a lot of experience on you, it turns out, and experience counts for something. And I've now almost literally, not quite yet, but I've almost literally been programming since before you were born. So, a few more years and I'll hit that point.
That's
not you, students. I mean, you kids, not you specifically. Okay, so, yeah.
Do we have to sign out?
No. Right? Or do you? What do you do for field trips? Yes? You sign off on field trips?
What?
It's during school hours. It's school-sponsored and during school hours.
You still talk to Brenda.
I'm going to sign up with Brenda. Oh wait, do you want?
I'm pretty sure we do.
That's wrong.
We're gonna be we're gonna be at the front desk anyway. So that's the bus will pick us up, right? So we can just sign out of the way. I can just give her a deposit. I think she prefers that. But I know we have to sign out, but I'm hoping I can do it all at once. It's just a lot easier. And I will sign you in as soon as we get back. And as soon as you are signed in, you are no longer excused from your classes. Right? So as soon as we get back, if it happens to be before the end of school, then typically it's supposed to be in your head.
Dr. Long, please.
All right, any other questions about Monday? When are we getting back? Interesting question. It fluctuates a little bit. A lot of it has to do with the D0 tour schedule. So it is hard to say. We can get back and we've gotten back before as early as 3 and as late as 4:30. And so it kind of depends on these D0 schedule things. It's the biggest part. So that's the least predictable part because D0 you have to split into groups of 10, and we have 45, 44. And so, yeah, anyway, that part will have to be, that's the part we have to work on. Okay, you can do whatever you want, but, yeah. Okay, moving on. You ready for physics?
No.
Woo! Let's go. Here's how it's going to work. I should be able to cover a good chunk of stuff today. That's good. So that we can cover all the stuff we need to, so that Tuesday can be review and go over homework. Sorry, you'll have homework due Tuesday. Otherwise, I have to do tomorrow, so let's have it due a week from Tuesday, coming off the lunch. Because otherwise, what we do? We need to do because the quiz is on Thursday, right?
Yes.
Yeah, woo! We love it. Okay, good. That was kind of amazing. That was good. All right.
Yes, this is
Well, that's better than I ever could. Okay, so what we're going to talk about is an interesting thing in quantum mechanics. Consider this.
Okay.
Here's an electromagnetic proton, for example. For more fun, let's make it a positron proton.
Why?
Now, when they collide, let's say they collide and bounce off each other. Okay, so these we call elastic collision, meaning nothing really happens; they just kind of bounce, which is the most common by far. Then they bounce out here, and you have some kind of detector surrounding it. You guys know how that works, right? And the detector can measure particle ID to figure out which one's which, right, and where it is. And so you can get the positron here and the proton here. Okay? So the way we do it is each particle, there's two particles here, right? Each one has its own wave function. So I'll call this particle psi1 and this particle psi2, right? Those are the wave functions that represent those two particles. And these positions they end up, I'll just call them x1 and x2. And the actual positions themselves is not that important, right? It's just a demonstration. So the way we can say is the result of this experiment is that you get psi1, the particle psi1 is at position x1, and the particle psi2 is at position x2. That make sense? I mean, it's kind of straightforward, right? They hit, you find where they are. It's just a little notation, right? Psi1 and psi2 are the two particles. x1, x2 are the places you detect them after they collide. Okay? Good. Now let's say let's say we're colliding two gold ions. All right. Did you guys come up with the name for your detector complex?
Should be the meme, but
I'll let it be a surprise. Okay, good. So now these things collide again, just bounce off, right? Nothing crazy. Like I said, the most common thing is that they just bounce off each other. Yes, because of that. Yeah. All right. So right now you get this. Now this is actually a different situation than this one. Why is that? Not because of particles. What did you say? So, what does that mean? Good. I don't know whether these went like this or whether they went like that. You see, I don't know whether this one ended up here or whether this one ended up here. I just knew a gold ion went here and another gold ion went here, but I don't know which one was which. Okay? This is actually quite important. And here's the thing, you're like, well, I mean, does it really matter? You don't know which one it is? Well, turns out that apparently it does. Here's why. Look, let's say we flip two coins, and I don't know which one, but I don't know which one was which. Well, maybe I don't know which one was which, but you could always identify them, right? Like I could flip a penny and a nickel, then I would know the penny got this and the nickel got that, right? Or if you're doing this with marbles, then you knock the two marbles together and they bounce off, right? Well, you just use two different colored marbles, right? Or you put a little mark on one of them, or you put a flag on one of them, or whatever, right? It'd be easy to tell the two apart. But imagine you're doing electrons, for example, right? You can't paint electrons red. You can't put little flags on them. You can't mark them with a Sharpie, right? How can you tell two electrons apart? We'll see in just a moment. But first of all, Jay said spin. In principle, you could align them in such a way they'd opposite spin, and then you would know. But what if you don't, right? What if the spin is just whatever spin? So then you have no information still, right? Then what happens? They collide, they bounce off, and you don't know which one went where, right? Yeah. Okay. Here's the thing. As far as we can tell, there is no way to know which one went where. It's not just you don't know. but there is no way to determine which one went where. So we end up with this thing that I think is a postulate, but a very important one in quantum mechanics, which is in quantum mechanics, identical particles are indistinguishable in principle. What does that mean in principle? Right. What does that mean? They're indistinguishable in theory. No, that's not what it means. Go ahead.
I was going to say, it's like whenever you're doing all your predictions, they're indistinguishable, but whenever you do the actual practical, they don't necessarily have to be.
No, it's the opposite of that. I know we use it that way most of the time. Most of the time, something is possible. You say such thing is possible in principle, but in practice very difficult, right? Like in principle, it's possible to, in principle, if you mix salt and sugar together, it's possible in principle to unmix them, right? To pull the salt and sugar apart from each other. In practice, very difficult, right? So that's one of the things that's in principle versus practice. Now, here's an example of something that is impossible even in principle. Okay? Also not possible in practice. Okay? When we say it's indistinguishable in principle, that means you cannot treat them like they're distinguishable and we don't know the difference. They are actually not distinguishable. That is to say, the wave function here is actually a combination of two things. There's psi1 going to x1, where we label them the same way, right? Psi1 can go to x1 and psi2 goes to x2. And that's one possibility. But the other possibility is what? You have psi1 goes to x2 and psi2 goes to x1. And each of these are equally likely. So, what do we do to show the overall wave function? Well, what do you have to do with that? What's that? Good. You can do this 1 over root 2 and this. Right? That shows 50% this and 50% this. Right? You have no way to distinguish between them. You see, when I say indistinguishable in principle, I mean the theoretical wave function is actually different. It changes when they are identical versus distinguishable particles. Also, by the way, if you want these to be 50-50, this doesn't have to be a plus sign. What else could it be? It could be a minus sign, right? You're like, okay, I guess, right? Does that make a difference? Yes. Okay, sure. Wait, what difference could it possibly make? I will explain. Good. Yeah. I will show you. But you see, when I say that the indistinguishable in principle, I mean that the theoretical wave function you write is a different one from the one that you write for distinguishable particles, right? It's the exact same situation, except that you cannot tell these guys apart. When you cannot tell them apart, you end up with a different wave function because of this ambiguity here is unknowable. Like, there is no way to know which one went where. Okay? Yeah. They have different positions, but you have no idea which one went where, right? So in that regard, they are indistinguishable. I know I have 2 gold ions. I know I started with 2 of them, and I ended with 2 of them, but I don't know which one ended up where.
But they can't be in the exact same.
Well, I mean, they could be. Why not? They're wave functions. They're just superimpose when they go over each other. So, no big deal. But the main thing is they don't have a position until you measure them, right? So when you measure them, yeah, you measure them in different places. What I mean by indistinguishable is I don't know which of these went to that position, right? That's the key part. I don't know which of these 2 possibilities is. I can only take a superposition of them. Why is that an issue? Simple answer, probability. Okay, let us review our probabilities. Let's say, for example, we want to flip 3 coins. Wow. I'm not really sure I'm writing. Let's say you take 3 coins and you flip them. Let's calculate the probability of getting, let's just do 2 coins, it'll be easier. Flipping 2 coins, what's the probability of getting 2 heads? All right, good. Let's calculate the probability of getting 2 heads. Now, to do a probability, you find all the different possibilities, and then you identify the sample set, they call it, right? Not sample size, isn't there? What is sample set? And you take the size of the sample set. Anyway, whatever. That doesn't matter. You identify the ones that fit your criteria, which is the 2 heads possibilities, right? So let's take a look. What are the different possibilities you can get when you flip 2 coins? Heads, 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 tails, tails, heads, tails, tails. Okay, good. So probability of 2 heads. This is the only one that has 2 heads. There's 4 possibilities, so it's a 1 out of 4 possibility. Now, we know this? Like, we're okay with this? Yeah? Okay. Why did this part ever bother you? Right? I think it should bother some people. Why heads, tails, and tails, heads are different? Isn't it the same thing?
They're in a different order.
Well, what do you mean the order matters? Why does the order matter?
Which coin you flip.
Okay. It matters which coin you flip, right? So there is, then I say, how come you have 2 heads, heads to balance that? You know? Doesn't it seem unfair?
Yeah.
Right? It doesn't bother you? And here's why. It's about physically distinct final states. So, let's say we flip, to be specific, a penny and a nickel. So that it's easy to tell the difference, right? Okay. One physically distinct state is penny has heads, nickel has tails. A different one is penny is tails, nickel has heads, right? You can look at those and observe the difference between them. Therefore, these are 2 physically different states. However, if you flip them and you get penny is heads, nickel is heads, that is the same state as penny is heads, nickel is heads, right? There's only one state that has penny is heads, nickel is heads. So that's why that one only counts once. Okay? Does that ever bother you? I don't know. That would always bother me. Well, but when you think of it, I don't know what the mathematicians say, but I think of it in terms of physically distinguishable states. You imagine 2 different coins that the heads, tails, and tails, heads really are different from each other, but there's only one heads, heads option that's measurably different, right? Anyway, of course, you actually try it. This is what happens. So that's the other answer. So that's good. Now, what if they are now identical coins? So identical coins cannot be distinguished in principle. That's to say, there is no penny and nickel. There's just 2 coins, right? And you don't know which coin is which. Then, what are your options? What are your options? Heads, heads. Heads and tails, in some order. And tails, tails. Okay? Where this one is the same as tails, heads because you can't tell the difference. You can't figure out one order compared to another. So the fact that they're indistinguishable in principle is important because that means there is only one heads, tails state here. Which means, what is the probability of getting heads, heads? 1/3. So the actual measurable probability changes when they are identical part ones.
But it's important to actually identical coins and flip them so the possibility.
What are identical coins exactly? Are they really identical? Do they have the same number of atoms? Theoretically, you could try that. They'd have to not only the same atoms, but the same configurations, right? Like every atom would have to be the exact same place, right? If you could do that, then you might actually end up with this problem, but you're never going to do that. I don't think it's theoretically impossible. I think it's just very hard. Yeah, it's not a perfect clone in this case. This is big enough that I don't think that would be an issue. I could be wrong. But either way, I know it's not going to happen, right? If you did it, maybe you would see this effect. That would be cool, but yeah.
But regardless of the fact that you can't distinguish head sales and tails heads, what if head sales don't happen twice exactly as tails state?
No. Because, that's why it's very important to say, you're still thinking, I can't tell the difference between, you're thinking like Emily says, look, I get 2 coins, there's no way for me to tell the difference between them, but I still get it 1/4 of the time, right? That's just your lack of knowledge, right? That is just a practical inability, the practical lack of knowledge. I practically have no way of knowing the difference. But theoretically I could, right? If I counted the atoms, if I looked at exactly where every, where every nucleus was, the lattice, right? I could tell them apart. What we are talking about is things that are indistinguishable in principle, which means that they cannot be told apart in any means. They are theoretically treated as the same thing. And so, because of that difference is a theoretical difference, a difference in principle, then you get only one outcome here. And this is not made up. We can measure this. And it changes when the particles are identical. I love teaching physics. Let me make a little chart that talks about the different kinds of things to deal with. Okay. Let's see a little bit of particles. So, for example, we'll have distinguishable particles. We often have names that describe the kinds of statistics that these different things follow. Okay, for this one, it's called Maxwell-Boltzmann statistics. Maxwell and Boltzmann both did a lot of work on thermodynamics, on figuring out how little particles move around and how to get like the overall behavior from considering little atomic movements. So we named this, we call this Maxwell-Boltzmann statistics. This is the regular world, normal things that we're used to, called the Maxwell-Boltzmann statistics. So in this case, the wave function looks like, for example, this, right? Simple, well-defined, only one possibility. And you have many possibilities. They all look like this, right? There's just one outcome. Okay? Good. Well, the next kind to consider is identical particles. But we'll see that there's actually a little bit of a distinction here, and we'll explain why we'll explain part of it. I'll put on the wave function first. Let's take that wave function and I'm just recopying it, but I'm going to do the one with the plus sign. Okay? Is that plus or minus sign really going to make a difference? Yes. So let's start with one with the plus sign. These particles, the particles that follow this behavior, were worked out at first sort of accidentally, not quite accidentally, but there was an obscure publication by an Indian scientist, an Indian physicist named Bose. One of the first Indian contributors to the field, and this being the early 20th century, people ignored things that Indians said. We still do, but we try to be quieter about it. We ignored things that Indians said, so everyone's like, yeah, whatever. So it got published in a pretty obscure journal, because they don't want to take it, but he did a lot of really, really interesting work. Fortunately, there was someone who did read it, who wasn't so bothered by the whole Indian thing, was more interested in the physics, and that was Einstein.
What is it?
And Einstein was like, oh, this is great. This actually does a good job of describing this quantum mechanical system we've been looking at. And together, we refer to these statistics as Bose-Einstein statistics. Because, Bose and Einstein came up with it. Right?
Einstein was a decent person.
Einstein is a very generous person because, he could have taken all the credit for himself, and who would disbelieve him? He's Einstein. But Einstein actually he was not a perfect person, but as a scientist, he was very good. He had a very strong moral framework as a scientist, and would not do something like that. And so he gladly shared the credit with this obscure Indian physicist, who is not the same guy as the one who makes the sound systems, by the way. Somewhat common Indian name, apparently. Because of that, particles that follow this law are referred to as bosons. Oh. You could have called them Einstein-ons, but you have to admit that bosons sounds better. Okay, good. So that's neat. Now, the other possibility is when you have a minus sign, right? Okay, that's the other possibility. You're like, plus sign, minus sign, big deal. Either one's a 50% probability because you square it at the end, right? Okay. But there is a difference. And the difference is important. It's quite noticeable, quite measurable. Consider the case. What happens if psi 1 equals psi 2? Let's say two particles have the same wave function. Okay, well, plug that into here, right? And for this one, you get 1/√2 times psi 1 x1 times psi 1 x2 because they're equal to each other, right? Plus psi 1 x2 psi 1 x1. And these two are the same and they'll add together and nothing really happens. Okay, great. You get something, right? No big deal. Now consider this one. For this one, you get 1/√2 psi 1 x1 psi 1 x2 minus psi 1 x2 psi 1 x1. Now, since multiplication is commutative, you can switch the order on these. And what does this one give you?
0.
This gives you 0. What happens when your wave function equals 0? What does that mean?
That can't happen.
It cannot happen. Good. The probability of it happening is 0. Right? Wave function of 0 means probability is 0. It means it cannot happen. So for these particles, there is a restriction that these particles do not have. Okay? And that restriction is going to manifest itself clearly in their behavior. Okay, so these particles were worked out by a pair of very famous physicists who both did a lot of important theoretical work on them and some experimental work as well. And so we refer to this as Fermi-Dirac statistics because Fermi and Dirac worked on them.
Fermi sounds familiar.
What?
Fermi sounds familiar.
Sounds.
The Fermi part, it sounds familiar.
Sounds familiar, yes. I sure hope so. We were just talking about going there next week. The original name of that laboratory near us was the National Accelerator Laboratory. When after Fermi died, they renamed it the Fermi National Accelerator Laboratory and honor his many accomplishments, as many contributions to particle physics. Fermi was awesome. He was the last person who was both a great theorist and a great experimentalist. And the last person who really did both.
Can't do it anymore.
It's just no.
It's so bad these days.
Yeah, no, it's just not very practical. It was hard at the time, but Fermi was really smart. Fermi was so good at predicting and like rough calculations of things that they named a whole category of problems called Fermi problems that are the famous one that according to rumor he asked prospective grad students, like someone wanted to study with him. He said, okay, well tell me, how many piano tuners are there in Chicago?
Oh.
Right? And he says, well, you should be able to make quick estimates based off, well, how big is Chicago? How many families are there in Chicago? How many of them own a piano? How many piano tuners are needed per piano? Right? And to estimate how many piano tuners are in Chicago. He could do that stuff so crazy well that he actually got a good estimate of the blast of the first atomic explosion of Mogador, New Mexico, by taking 3 pieces of paper and dropping them at different points as the shockwave hit, and looking at how far the pieces of paper were moved by the shockwave when it reached them, and from that got the yield of the bomb in his head to within about 10% of the official yield calculated. Yeah, because that's Fermi. He was, as the kids say, a boss. So, Dirac was also cool too, but he also gave us the bra. And so these are now called fermions. Okay, so you have fermions and you have bosons, and this behavior shows you that plus or minus sign makes a big difference, right? And that big difference between them is encoded in the famous chemistry idea, the Pauli exclusion principle. Okay. Pauli exclusion principle is very important, and what it says is no two fermions can be in the same state. Okay? State, remember, is determined by your wave function, right? That is the state of your particle. Now, state includes position. So if you have two fermions that are identical except they're in different positions, that's fine. No big deal. But they cannot be in exactly the same state. Notice that's not intrinsically a big problem. Remember, they're all waves, right? Waves can go right through each other and it is not a problem. 20 waves can all meet at one point and it's still not a problem. They just keep on going, right? But fermions are different. You can never have them in the same state because when they are, there's that minus sign that shows up, and the minus sign makes the probability go to 0. And so fermions have this requirement that makes the world a whole lot more interesting. Does someone want to tell me what the major consequence of the Pauli exclusion principle is in chemistry? Someone should be able to. Someone should know this.
Chemistry is for losers.
It has to do with what with orbitals. Good. Tell me more about orbitals. No two electrons can be in the same state means that you cannot just pack all the electrons into the first orbital. You have to keep on expanding into further and further orbitals because there's no room for them in the lower orbitals because the Pauli exclusion principle forbids them from being together. If electrons were bosons, it would be no problem. You just put, the chemistry would be super easy. There would be no orbitals. Everything would have n equals 1. It'd be great. Everything would be in the s orbital. It would be so nice. But it'd be very boring. Like all elements would be virtually identical. So, also we wouldn't exist, so there's also that. So like the Pauli exclusion principle is major. It has a lot of other interesting things too. Like in white dwarf stars, there's a cool thing that happens when gravity is pulling the particles together. Normally in a star, what happens is gravity pulls them together, then the force of the fusion explosion pushes them apart, right? In a white dwarf, there's not enough heat to cause fusion, so the gravity pulls them together, and there is no fusion to stop it, so it just keeps on pulling them closer and closer and closer until the particles start getting really close, but they're fermions. So when they start to get really close, they're like, wait a minute, we can't be in the same state, and so they actually repel each other by the power of math. Like there's no force. There's no it's not electromagnetism, it's not the weak force, it's just the fact that fermions cannot be in the same state. So when they get too close, they're like, nope. And it actually happens. It's called degeneracy pressure, and it's been well measured in the laboratory. And it's what stops degeneracy pressure is a horrible name. It sounds like your ne'er-do-well friends trying to get you to take drugs. But anyway, the degeneracy pressure, right? But when they get too close, they will stop and they won't get any closer because they can't. Right? So that minus sign is very powerful. It actually is a thing. I know, right? Isn't that weird? It's sometimes referred to it as an exchange force, but it's not. But it's not like there's no force carrier for it. It just happens this week. Just like the wave functions cancel out. They're like, oh no, can't do that, and they stop moving towards each other.
I will resist the temptation of drugs by the power of math.
There you go. That's right. No, except it's the other way around. That resistance is degeneracy pressure. So I don't even know.
Resist the power of math with drugs.
No, I don't even. Let's not go there. That's not all right. So first of all, this case here was identical bosons. How is it different when we have identical fermions? What can you tell me about the coins in the case of identical fermions?
Wouldn't the only option be heads, tails?
They can't both be heads, right? Because that violates the Pauli exclusion principle. They'd be in the same state. They also can't both be tails. So what is my possibility? Heads, tails in any order is the only possibility. So the probability of getting two heads is 0 if they're fermions, because they can never be the same. So bosons and fermions have very different statistical behavior too. It's true. All right, so what makes a boson and what makes a fermion? You guys ever seen Peter Pan?
Yeah.
The original Peter Pan. Have you seen it recently?
No.
It is the most stupendously racist film ever.
Yeah.
It's like
Oh,
amazing.
yeah.
It's like, oh my goodness, like how can you, like, wow. Like, yeah. It's amazing. Also, Captain Hook shoots someone and kills him. He shoots and kills someone. He's off screen. The Disney one. The Disney one, yes.
I didn't realize that.
Yeah, no, it's like, oh my goodness, like, yeah, no, there's a YouTube channel, it's Oddish Trailer, if you guys ever seen it.
Oh, yeah.
They're one for Peter Pan that points out all these things, and I'm like, oh my goodness, and it gets like progressively worse and worse, and I'm like, wow, I have forgotten about all this. And I'm like, I mean, that it's like they point out, like, the parents are, the kids are so neglected that their parents keep running off, and they're raised by a dog, right? Because it shows like the dog pouring the medicine for them and stuff like that. And it's like, oh yeah, that's an interesting point. Yeah, I believe it. Just look at all the racing parts. Probably
It's
still.
more like London, like modern day, like London. It's probably this can be.
Oh, a more recent one.
Yeah.
Because there's the original, I mean, the Disney's not the original, the recent.
All the original.
And then so there's one part where it like starts showing in that outro, it starts showing like all these clips of all these like racist parts from it, and it's like, oh no, I forgot about that. Oh, this is awful. It's like stop, show another movie, and then it starts flipping to all the other racist parts from other old Disney movies. So it shows like parts like all the crows from Dumbo, and which are like, wow, watch them again. Oh wow. And the We Are Siamese song from Lady and the Tramp. Like, wow, you can't do that anymore. And then the last one is what I had totally forgotten from the Aristocats, which has this like cat and a piano with this stereotypical like Chinese cats in his hand going like 8 full yolks I saw. Whatever. And like the piano with chopsticks. Oh wow, I really forgot about that too.
You can't really rewatch Disney classics. You can't really watch those movies by change because it's like,
wow, no wonder we're all racist now. Okay, sorry, I didn't actually tell you the answer.
how do we get onto this subject?
I'll give you a quiz about like which of the following is the most racist movie. That maybe will give an answer. Give 5 examples.
And can we have an open note? If we do that, can we have an open note test and just watch the entire movie?
Yeah. You know, if it weren't for the fact that I would lose my job, it'd be fun to write a problem on quantum race. But anyway. But I like my job actually. So,
you know we have 60 seconds, right?
What? No, we have the bosons. We've got like 3 minutes, and I only need to tell you this one thing, which is bosons
Access 54.
have
I'm so confused.
integer spin, and fermions have half integer spin. Okay, that's the definition. Bosons have integer spin, fermions have half integer spin. And bosons follow this rule with a plus sign, fermions have follow this rule with a minus sign. Now you might be like, wait a minute, I don't really see why those two have to go together. Well, that's fair. The reason that they go together is a very complicated proof that Dirac did called the spin statistics theorem. And I cannot possibly, I tried to figure out ways to give you like a quick hand wavy version, and no, I don't really understand it too well myself. Basically the way it works is this, that there are mathematical differences between having integer spin and half integer spin. For example, you notice that integer spins always have an odd number of possible n values, but half integer always have an even number of possible n values, right? There are mathematical differences. If you follow mathematical differences far enough, then you discover that you end up with one being, they call anti-symmetric, and one being symmetric, right? But the following them to that degree is very, very hard. So I'm afraid you're just going to have to memorize this. Integer spin means bosons means plus sign. Half integer spin means fermions means minus sign means Pauli exclusion principle. Okay? All right. I'll probably go ahead and post more, but we don't need to go over it tomorrow. I'll be on your slides tomorrow. And should it chance that your final project submission quite done yet. Let's make sure to get that done. All right. Can you please contact the people who are in the group who aren't here about the slides? So Micah, Riella, Matt, please, if they're in your group, please contact them to make sure that they get teams coordinated. I've talked to some of them already.
我想失望，给我失望，给我失望。
No idea.
Oh, I thought that's what swastikas for a second. I was very
For the winter?
Gotta stock up. I don't get it. I don't get it. Oh, never mind. I see it.
No, I just.
I didn't see the bottom.